Sarah, look at that. That's the only time they cut out for me is when I say class is over.
Right.
That's pretty impressive. So guys, Sarah, was, my internship student, the last 2 semesters, and, she did a heck of a job. She really understands muscles and function but she understands it in her unique way. I mean, it's all the same stuff, but I think she has a really unique perspective. And I also thought it'd be important to have a peer, someone your age that can kind of also add some legitimacy and some insight to how, she studies, how she understands. Um, so what I want to get to is one little piece of applied info that I didn't get to, even though it's nothing new. It's that cross-sectional picture that I had up on Moodle. And Sarah, she saw it immediately. She's like, "Oh, the merry-go-round." Exactly. This is the merry-go-round that's in your head. And if you have a muscle on the right side of your right ear pulling forward and close to your left ear pulling back, they are going to force couple, meaning two different linear forces that are working in the same rotational direction. Just like again in the merry-go-round, if we're trying to spin the merry-go-round and Sarah's on the other side, we do not want to pull the merry-go-round in the same linear direction. They're going to cancel each other out. She needs to pull one way, I have to pull the other way to make the merry-go-round spin the same way. So that's how kind of muscles work as force couples, and they can cancel out. You can see how the pull would cancel out frontally, cancel out sagittally, but work together transversely. Really important if you're trying to look quick, right? Whoa, what's over there? You need muscles that can work together to spin the merry. Okay. So Sarah, what I'll do, insights.
Like if I had some ropes tied to my ears, and I had one person, we're trying to spin my head to the left, and one person was pulling me this way to go this way. One person would be pulling me in the back. Like you said, it's stronger when you have two people on the other sides of the merry-go-round, versus just one person trying their hardest. Like, let's say for some reason this muscle gave out, couldn't whip my neck that way. They're working together. So front, right, back, left. That's how I think about it in simple terms.
Absolutely. So guys, for this review, what we'll do is, Sarah will give some general advice on what worked for her. You just took this class. Yeah.
A year ago.
Yeah. And so, she'll give some general studying advice. The physics part, we'll talk about, we'll clarify. Did anybody happen to see that video that I sent, kind of talking about things? But I sent you a video from last semester that kind of clarifies some things too. There's going to be 33 questions. I'm going to round up to give you that extra point for 100. I'd say 13 of those questions will probably be on cervical. And if I were you guys, I would be like, give me 20. Because again, it is what it is. You can't say the right sternocleidomastoid does something that the left it is. And so that's roughly the breakdown. Sarah, how did you prepare or study when you started going over circles or muscle function?
So we didn't do circles until the third test. Whenever I took it, so we started very physics based.
Yeah.
And I don't even think y'all are being tested on everything that we were testing. No. So I'm gonna take back some circles though. Anytime we would be talking about muscle, so because you post the circles prior to the class, right? I would have that circle out, and as he's doing the motion, it was my iPad. I have my iPad not like this, but like flat, watching and moving with him. So, okay. But I just think that you're not going to have him talking in your ear about the surface on the test. So that's the type of practice. I mean, you already, in 310, you learned the motion. Now you're learning how the muscles are making that happen. So if you see the circle, those two at the top are here, and those two at the back are here. So I don't think that this is easy to comprehend if you're looking at it like that. But if you can imagine it like a disc, got one of those? Yeah. Like a disc here, and those two are at the front of it, that makes more sense that if I want my cervical to flex, I would need the two at the top pulling down
Muscles can only pull.
Muscles can only pull. That's a great true or false question, right? So that he right now is like a spine, right? Like, that's my eyes. That's what is what I'm saying. Like, he's like this right now. So then just knowing that cross-sectional is here, the muscles are surrounding and pulling in ways that are going to lead to the motions that you already have. I think that that's the best way to approach the circles.
Anterior muscles, posterior muscles, right side of the spine, left side of the spine. And then you go to PE, who's trying to spin the merry-go-round this way, who's trying to spin the merry-go-round that way.
And then if you see, like, that force couple, again, you can see it like the merry-go-round here and there. They're not, the arrows don't look the same, but they're going in the same direction. So that's how they're pulling together, making those faster movements. And I understand that because again, if we didn't have this one test, I'd be very tempted to not use the circle or not get used to the circle if this was the only one I had. Unfortunately, this is the easiest one. So in my opinion, go ahead and get familiar with it, because whenever you get to the hip, it's blown up with muscles. And you're going to get confused if you're trying to memorize that list down here. This list, it's pretty self-explanatory.
Yeah.
But this test would be, like, in my opinion, the only test where the list is going to work.
Yeah.
I think that getting used to how practical this circle is your best guess. Because let's say we're taking the test, right? And first thing you're gonna do is analyze the motion, right, of the two pictures. Let's say it goes from here to here. And you say, okay, so I had cervical flexion, then I must need my flexors. You just covered these up. Those two are your possible answer choices. And he can ask for both of them, or he can ask for one of them. So already you can cancel out possible answer choices by using a circle, and then you're moving on to the next thing. If it's left bending, then you're covering these answers, because it has to be left side muscles doing that motion. Does that make sense? So I really implore you to start getting used to the way that this looks, especially for lower body side.
So some of the things that this circle can tell us, or the list, again, I'm never going to ask you to draw it. But if I ask you functions of a specific muscle, what does function mean? Function means, how does it pull? How does it pull? Not necessarily specific motion, because we know that through different contractions, you'll have different motions, or no motion at all, right? In other words, even when you're sleeping in the middle of the night, your muscles are constantly pulling in directions of motion. That's what tone is, resting tone. So if I ask on the test, what are the functions of the right sternocleidomastoid? You just have to remember, how does it pull? And how does it pull is determined by how does it cross the joint. So if you know that the right sternocleidomastoid is an anterior crossing muscle, so it's a flexion puller, it crosses on the right side of the spine, so it's a right lateral puller. And when it plays outside for PE, it's trying to pull right ear forward. So it's pulling in a direction of left transverse cervical rotation. That's how it pulls. Now, it will cause those motions, but only when it's working how? The answer is isometrically, eccentrically, or concentrically. Awkward silence. It's not where we want to be right now. Concentric. Thank you. Concentrically. So the point is that the muscle pulls the same way all the time, regardless of the contraction. However, in terms of influencing motion, the type of contraction matters. You can't have it any other way. Too many times it's this muscle does this motion. No, it's this muscle does this motion through the context of the contraction that it works with. Extensors can do flexion when they're working eccentrically. Extensors can do extension when they're working concentrically. But if I ask you for function, that should be the easiest question. You want me to ask 33 function questions, because the contraction doesn't matter. It's just, how does it pull? Why is a hip flexor called a hip flexor?
Well, ironically enough, when you pull a hip flexor, you are extending because it has to work eccentrically to slow down the extension. But a hip flexor always pulls in the direction of hip flexion, whether it's working concentrically, eccentrically, isometrically, at rest, it always pulls this way because it always crosses the hip in front. So function has nothing to do about contraction, it's just how does it pull? Right sternocleidomastoid, flexor, right lateral, left transverse, left erector spinae, extensor, left lateral, left transverse. Left sterno, flexor, left lateral, right transverse, because that's how it pulls. And if you learn function or pull with your circle, great, you can have a lot of questions answered by one visual. But if you're not a visual, I understand. That's why I just make sure we're all on the same page. What does the right sterno do? What does the left erector do? What does the left sterno do? Muscles can only pull.
Here's function questions, stretching questions. Are they still things are?
Oh yeah, absolutely. Fair
So
game.
stretching, I don't want to put a muscle in its function position if I want to stretch it. So if if you like this, again, I lead with this, you're gonna save yourself some time. But again, if you like this, and you notice that the neck is in an extended position, well, if I'm extended, then I'm not stretching my extension pullers. I have to be stretching the opposite of what I'm observing. Trying to make sure I'm saying
Absolutely,
it
no,
right.
absolutely. If you're extended, those 2 points that pull back there have to be shortened. You're shortening the distance back there, and you're lengthening the distance here. And if you do it, take 1 second to look up, you feel the stretch anteriorly because these 2 points are getting longer. So how do you stretch cervical flexion pullers? By extending. How do you stretch cervical extension pullers? By flexing. How do you stretch left lateral pullers? By bending to the right. How do you stretch right lateral pullers? By bending to the left. To me, that's instead of a 1 foot putt of function questions, stretching questions should be like 3 foot putt questions. Like, give me all the stretching questions. How do you stretch a hip flexor? Not by flexing the hip, by extending the hip. That's how you feel the stretch in the front pullers. It's the same concept. The one curveball that I will say is that those darn force couple transverse rotators get tricky. Because again, when you look to your left, your instinct is to want to say, I'm stretching the sterno on the right. You're stretching something on the right, but it's not your sterno, it's your erector. Your erector puller is being lengthened on the right side, and you feel that stretch here. But your right sterno is actually getting shorter. The left is getting longer.
That makes sense again with the opposite of the function.
Absolutely.
Right, still there, so that's still in trying to achieve.
Identify your position, just like we did in 310, and say, well, if this is my cervical position, then the muscles that pull that way can't be lengthened. And the muscles that pull the other way must be lengthened.
It's like the same thing, I think a lot of y'all just did 310, the majority of y'all did. Then it's that ABC thing that we were doing, we have to figure out what the external force is wanting us to do, therefore we need the opposite of that, we don't need the thing that's gonna cause that. And now it's ABCD, doing the work, who is that muscle? So I'm worried, like tonight, you should be stretching at some point if it's test week, right? So get into some stretches and be like, have your circle, have your list, and be like, okay, I'm actually not just stretching my hip flexor or cervical flexors, I'm actually stretching my right and left sternocleidomastoid. That's what but get comfortable doing that, because that's how the test questions will be. It won't say cervical flexors. Like, it's going to be the names of these muscles, and I just want you to be comfortable with them. So, especially with that force couple thing, knowing I say the force couple with, if I'm looking to my left and it's my right sternocleidomastoid but my left erector, I think about my left erector first because it's in the name. If that kind of helps you, like if I'm looking to my left erector spinae did it, and therefore my right. That's how I think about it. Just because I like
To clarify, what if it wasn't a stretch question? What if I just said, to Sarah's point, you just look to your left? So go ahead, you just look to your left. Now, do you have any force that's trying to make you look to the right or to the left? There's no external force. You're not resisting anything. So if you look to your left, you have to have concentric contraction. You have to have those muscles that pull that way shortened to make you look to your left. Now, the same muscles can't push you to a stop. So that could be a separate question. Which muscle stopped you from looking to the left? But if I just said, which muscles made you look to the right or made you look to the left, that's something you should be able to answer. If you make yourself look to the left, right sterno, left erector, look this way. You look to your right, left sterno, right erector. That makes sense?
Dr. Campbell, is stopping muscles, is that all this test?
Because it's eccentric.
Chart, so that's fine.
Yeah, because it's eccentric.
So I think about stopping as in, like, I think about it putting on the brakes.
Putting on the brakes.
Because you're trying to stop. So you're just like if somebody pulls out in front of you, you're trying to stop. You're having to put on the brakes, and you do that. You don't put on the gas more. You would put on the brakes. So that's how I see it.
Muscles can't push.
Right.
So in 310, we would do this example. You remember that? Where we went transverse, where there's no external force. But if I need to put on the brake, I need muscles that are pulling this way. Because muscles that pull in can't pull and push. I gotta turn off the muscles that are trying to clap and turn on the muscles that are trying to brake. You feel it. So it's the same concept. Gas, brake. Gas, brake. Gas, brake.
Yeah, no problem. All right.
Yeah, absolutely.
Yep.
What I'll also do is reference you to posted lectures. So, muscles, motion, and contraction. This is a very important PowerPoint to pull up. This is where I go over everything in detail. And, so A plus B is equal to C, and I'm gonna let Sarah, talk about it, is muscles, motion, contraction.
Yes.
But I even explained how a work equation turns into A, B, and C. Work is force and distance. And so what about in 310, we would use work, physiological work and contraction interchangeably because it's the same thing. And so I explained how we get to A, B, and C, and we solve for A. A is your agonist, right? Who's working, because we ask ourselves why it needs to be working. We observe B, which is motion, and we solve for C, which is the contraction. And then I give some examples. Go ahead, Sarah.
Yeah, so this is how I would do most of my questions. I would start off with, like for example, right now, gravity is trying to pull my head down. So I'm using my extension pullers to keep my head up. So my external force in that example would be, gravity is trying to cause cervical flexion. Therefore, I don't need my flexors as my agonists. I need my cervical extensors. And then what do you observe? Am I doing this? Am I doing this? Or am I just like holding it isometrically? So let's for the body motion example, let's say I'm doing this. Then it would be my extensors doing cervical extension. If they're both doing like the same sounding thing, it has to be concentric. My extension pullers doing extension through concentric contraction. But if it would be this way, it's still my extensors because gravity's still trying to pull me this way. I have not needed my flexors once. So it'd be my extension pullers allowing flexion eccentrically. And then if I'm holding that position, it has to be isometrically. So that much we did, we have some experience with. Now it's just, we're seeing our agonists. So we look at our circle, we look at our list, and we say, okay, if I need my extensors, I need my left and right erector spinae muscles.
That was all in the last few classes. That was a lot of these examples. That's ABC. Muscles influence motion through contraction. Too many times, contraction, y'all never been taught how to see contraction. Y'all taught what it is, and I'm sure most of these majors can like define it. But can we apply it? Do we know how to see it? Can we set up environments to do it? Because sometimes when you're working with patients, there's going to be contraindications to certain type of contractions. Or there's going to be indications to certain types of contractions. We can't play fast loose. You have to know I'm working my elbow flexors eccentrically, or I need to just working concentric, right? So we need to be able to apply these different phases. Muscles influence motion through contraction, A, B, C. So to Sarah's point on this one, just something different, right? I play process of elimination. Maybe you do it differently, but I like to rule out who it can't be so that I can see who it needs to be. So the person is here, that plate is trying to bend them to the right. The last thing I need are muscles that are also trying to bend to the right. Right? The plate's trying to bend them to the right, so I need left lateral pullers. That's my agonist. That's my A. Well, here I would need left and
Yes.
Yeah.
Yes.
yes. Yeah, absolutely. Absolutely. Quick, and that's manual muscle stress. So like quick, if you have a shoulder problem, watch your feet, arms out. Don't let me push your knees in. You need muscles that are pulling out. Don't let me push your hands out. You need muscles that will stop. It's the same concept. If gravity's trying to do this, I need muscles that are pulling there. Are there exceptions? Sure, but they're super rare. That's like sprinting or doing something where you have to go faster than gravity. Gravity's trying to extend you, but when you're sprinting, you need extensors to go faster than gravity. But most of our activities in daily living are muscle agonists for opposite directions of external forces. So we identify the agonist, just like Sarah said, then we observe the motion, and the contractions prove the contractions given to you. If you know any two variables of a three-variable problem, then you know all three variables.
You can figure it out.
Muscles influence motion through the context of contraction. So if I could figure out my agonistic poles and I know motion, contraction is given to me. And that was the other day in class when I was like, dip and come back. Find the agonist pole. Pole is so important because it translates into all angles. I need left lateral benders. I need left laterals. Who are those muscles? The stuff on the left side. Left sternum, left erector. But when I get into contraction, those things don't tell me pull, right? So what I want to do is when I get into contraction, I want to come back to the agonist as a group and say left laterals. I see left lateral must be concentric. Left laterals, I see right lateral must be eccentric. That's how I would do it.
I think that this is just like you did on test 4 through 10, how you were writing probably the most you had ever written on a test. That didn't leave you. Like I would write on this test because you have a cheat. Like it's going to be A plus B equals C, you know? And you can get confused, but I mean, you don't necessarily need this for stretching, right? If you see that the neck is the cervical is in a flexed position, I must be stretching my extensors. So like I think this can be hard if you make it hard, but it can also be really easy if you tune into that. Like use the things that he said and like the props that you know to use kind of idea. Did you still have a question?
It was more like gravity affects that 100% exists.
Is gravity a factor? Yeah. So imagine like we had like a dumbbell and we're doing squats. I know we're not there yet, but just the idea of it.
Or we could be there for agonists, not specific muscles.
Right, yes, it's yes.
Talk about the group.
Like you know that weight is trying to pull me down, right? But I can also not have that weight and be doing like air squats, you know, like just body weight squats. And I'm still working the same muscles because now gravity is my external force. I mean, gravity's still trying to pull me down with the dumbbell, but that dumbbell is now a weight. That weight is trying to cause something.
It's like that contraction like eccentric, one out of out.
Yeah. So eccentric and concentric, it can get confusing, but if you start with that external force, if you make it confusing, right? That external force, and like, I'll put an example up here, so maybe after class you can take a picture of it. But if that external force is trying to cause gravity, is trying to cause cervical flexion, it is constantly trying to cause cervical flexion. Therefore, I need muscles that pull in the opposite way. So I'm going to need my extensors. And if now I already know my external force, I don't really need to go back to it. If I need my extensors and I'm observing flexion, which is exactly what my external force is doing, well, then it has to be eccentric because they're not the same thing. Extensors doing flexion, they don't pull that way. No,
Solve
it
for
depends.
contraction.
Right.
Contraction is solve for.
It depends on what he's asking too.
So let's use this one as an example, all right? And I also want to say to the jury, this is why, this semester when I was like, guys, catch up on your research. And I said, hey guys, Lindsay's gonna be here at 7:30 in the morning practicing with some stuff. This is why I said all this. What's grounding gravity trying to do to the knees? Is it trying to flex you or extend you? Like if she relax, we can do a thought experiment. She turns off all of her muscles. What's going to happen to the knees? They're going to flex. Gravity and ground trying to flex you like an accordion, right? The last thing you need are flexion pullers. You don't want flexion pullers. You pull yourself off the ground. You need extensors. You need extension pullers to go against ground and gravity trying to flex you. Who are those muscles? We'll get into that. Everybody's in the quad. Well, who's in the quad? What's in that? What's in that boy head? What's in that group? But the concept that if something's trying to flex you and I'm trying to resist it, I need something that's trying to extend me, go against it. This is the trick. Once you identify that you need extension pullers as your agonist, then all you got to do is, well, what motion am I having? Because if the motion is in the same direction as my muscles, that has to be contraction. And if the motion is in the opposite direction of my muscles pull, that has to be eccentric. So if she's here and you know that I'm working extension pullers and I observe the extension, extensors do extension only through concentric, shortening while trying to shorten while resting some. And if she's here and you observe flexion, the only way extensors allow flexion is through eccentric. That elevator lowering you down is still pulling up, allowing you to go down nice and controlled. So something pulling up is letting you go down. That's weird. And that's where eccentric gets its name.
Well, I guess the reason why thinking about eccentric, like, for instance, like, me personally, if you have add another picture, she's one, you know, that's why, like, me personally, more. So I would say, I don't like these, those little like fancy, why, but she. So it's like,
This is analogy, and the camera's not on. This is what just happened right there. Not for you to change up. You can't, because it is not your fault. Your brain is so used to thinking specific muscles with specific motion. And I'm trying to recondition your brain to not do that, because when we're talking about the knees and the hips, those are two different joints, right? So the hamstrings, we're going to teach you this, but the hamstrings cross the knee in the back. They're actually knee flexion pullers. They're hip extension pullers, but they're knee flexion pullers. So at the knee, we don't really want anything that's trying to pull my feet up on the ground. Does that make sense? We need something that's trying to drive my.
oh, I was on up my leg down, so.
Yeah. So you're still gonna need, and you know this, you feel this, when you're going down, you're still pushing down. In fact, you're pushing more. You kind of let off on the way, like when you think about doing like the max on your squat, at the top, you're like, you're catching your breath. Jelly cars, right? That's when you're really efforting at the bottom. Because your knee extensors and your hip extensors have to slow down your flexion. Well, it's when muscles only pull, and pull is tension. But when you're providing tension above rest, what's happening to those 2 points? If the 2 points are being lengthened while trying to shorten, That's eccentric. That's really cool. When the 2 points are being lengthened while still trying to shorten, that's eccentric. When the 2 points are coming together while trying to shorten, that's concentric. And when the 2 points have the same length while they're still trying to shorten, that's isometric. Eccentric is going to put on brakes. But what we don't want, this is what we don't want. We don't want to say extensors on the way up at the knees, flexors on the way down at the knees. That's not how it works. You know, when you're doing curls, you're working the same muscles the whole time. You wouldn't say, you just popped it in the right foot. You wouldn't say I'm working bicep and tricep. It's the same concept. Same external forces, same muscles. The different motions is because of different contractions. And that's what I'm trying to apply to teach you.
Going off that real quick, this would just be for one direction that you'd be going. If you're going down into the squat, you would do this. And then when you're coming up in the squat, your body motion is now changed. So if we're going down, eccentric, but if we're coming up and these two, we're having extensors doing extension, now we're concentric. So there's 2 phases, if that's what it was kind of also being used.
And that's why we try to solve for the contractions. So we'll try to make it less confusing by saying, if you know this, and you know this, then this has to be this. If you know that number is 5, and then you know it's added by 3, you know this has to be 8. Chance?
I was gonna ask something related.
Please.
Trade movement company.
Trade.
Yeah, trade.
Absolutely. I'm just gonna give you the important stuff,
Yeah.
what you're gonna have to know. And also, Chance, you're having a study group tonight
Yeah, so,
at 7 o'clock in the computer lab.
yes.
Okay. Guys, this is the so what about trade, right? We have our Cartesian plane, positive x, positive y, negative y, right? Okay. Rarely, forces in motion happen in any one of 4 of these points, because in the real world, there's 360 degrees, and there's only 4 points on that grid where it's all in one direction. Majority of the time, it's station. Rarely do you just move north, south, east, or west from triangulation. In the real world, it's northwest, south, east, right? It's some combination. So this applies most of the muscles. But in the trigonometry part, what all I want you to see is that angles and sides have a proportionality. As I go from 0 to 90, I'm getting less and less and less x component and more and more y component until all of it is y, none of it is x. And if I keep going, I'm getting less and less and less y, more and more x until all of it is negative x and none of it is y. So on the test, I think all I emphasize in the videos is if I give you a magnitude, that's an amount, what do you measure? Are you measuring velocity, speed, are you measuring force? And at a certain angle, again, nothing is usually all in one direction. So if I have a force of 500 pounds at an angle of 30 degrees, all I'm asking you to see is, oh, some of that is positive x and some of that is positive y. It's in quadrant 1, it means I'm like northeast, right? And the other trick is, what's halfway between 0 and 90? 45. So if I'm at 45, I know that I'm just as much north as east. My x and y components are going to be equal. But if I'm steeper than 45, it's more y than x. And if I'm shallower than 45, it's more x than y.
That's what you calculate with.
You don't need to calculate.
It would tell.
What's that?
So we're gonna have to file the extra long as a machine.
We will, when we do, we're doing it right now.
Yeah, I mean.
We're doing it right now. So like the sternocleidomastoid mastoid has an angle. Some of that pull is here, some of that pull is here, some of that pull is there. So that's how we apply it. Remember though, for the trigonometry, they're not linear. Because of the squareness, they're curvilinear. And I think that's one of the biggest lessons I'm trying to teach you, is that just because a muscle in this case might be steep, doesn't mean it doesn't have more cross pull than you think. Because those components are square. It's exponential, it's not linear. Sometimes, I'll give you an example, we're gonna have a muscle called the tensor fasciae, and it runs very up and down, but it has more cross pull than you think. And it has more flexion pull than you think, because it's square, because it's not linear.
So to say, like, the center cloud mass or whatever,
That's all right.
it doesn't get to choose whether it's gonna turn this way, go this way, or go this way. It's always gonna pulse kind of like this.
Absolutely.
But when other muscles are going, it'll decide.
Who we choose, that's a really good way to put it. Who we choose to work with, like, it's like having different group projects, and based on what we need is who your partners are gonna be. But absolutely, if I think in class I said, if I could, I said a buddy of mine is a nurse anesthetist, he could nerve block certain things, so you don't have to go into anesthesia. If I turned off, if I was, laying down and I turned off all my muscles and I just stimulated that, it would do this. Absolutely. But if I work the left erector at the same time, you're gonna get this. And if I work the right erector at the same time, you're gonna get this. And if I work the sternum at the same time, you're gonna get this. The muscle, you know how people say muscle memory? Muscles don't have memory. They're just responding to stimulus. So yeah, I recruit it, it's gonna pull more. But who I choose to recruit it with is gonna determine what gets canceled out. So the main things on the trigonometry, if you go back in that review, I tell you exactly what I'm gonna ask. And it's to try to show you there's a relationship between resultants and angles and the components that make it. And I try to show you, doing some trig just to show you that it's true, right? Like, well, how can 10 degrees change create like 40 degrees change in the component? Because of the square, c squared, b squared, c squared. Yeah, levers and pulleys. So levers and pulleys help muscles be better at certain things. I think in the lecture I said, guys, you're only accountable. Here are the 5 classes of pulleys. But remember, there's the engineering part and then there's the bioengineering part, right? So for us, really, we're interested in first, thirds, and fifths. First would be like the leverage is where for the pulley, the bone is literally encased in the muscle tendon so that it can get a better pull. Thirds is where the muscle wraps around like a condyle or a bone that's outside of the tendon itself, but it still gets a mechanical advantage of pull.
Do we have to go certain examples like,
If I say no first, thirds, and fifths, I'll at least know the examples I gave you in the materials. And then the fifth is where our muscle serves as a pulley for another muscle. Like our brachialis for our bicep or our soleus for our hamstring. Levers are trade-offs of mechanical advantages, functions of simple machines. And it goes back to like in 310 when I gave you the different bone classifications. And it was like, guys, I'm not asking you to memorize a bunch of words, just know the advantages. Flats are good for protection. Longs are good for movement, and shorts are good for summation of motion, dissipate the force. So for levers in our body, firsts are incredible for balancing 2 or more forces. So if you think about balancing on one foot, you have inverters on one side of the teeter-totter, everters on the other side of the teeter-totter, and the subtalar joint is our axis, and it's helping me balance. Firsts are when the axis is in between multiple forces, literally like a teeter-totter. The examples in the materials, the cervical, which I think is kind of ironic, right? Here's our axis. We have erectors pulling back here. We have gravity trying to pull right there. What a great way of balance to keep our eyes level. Process information. Also, first-class levers redirecting applied forces. Meaning, you go back through the lectures, I say this. I pull the base of the skull back with my erectors and the front of my head goes up so I can look up. How do I look up? I don't look up by pulling up. I actually pull something back here so that I can look up on the other side of the teeter-totter. Here's the teeter-totter, I pull this side down so this side goes up. So that this side can come up. Those are advantages of first that I emphasize, those, and I emphasize is the only thing I'm gonna ask you. For our bodies, first really come into play today. Thirds and seconds, the trade-off of speed and torque, right? The advantage of one gives you a disadvantage of the other. If my muscle is inserting close to the axis, I get more and more advantage of speed and less advantage of torque. And then if my muscle inserts further and further away, I get more of an advantage of torque, but less of an advantage of speed. And I think in class I gave you these like a ladder with different rungs that you can, like say, hook and pull. So if the ladder was super heavy, there's no way I'm going to raise it up, pull it close. But if the ladder was light, you can make it fly real quick. But if the ladder's heavy and I have to attach it way on the other end, I can raise it, but it's going to come slow. So the reason I'm giving you that is because as we look at muscles, maybe not so much in the cervical because it's mostly kind of like a merry-go-round, but when we get into some of these appendicular muscles, you're going to notice, wow, some that close to the shoulder go very far away, and some go close and some go midway. That's all mechanically advantaged. And when you see certain muscles that have the third-class advantage of speed, you're going to say, wow, so they must have a disadvantage of torque. And those are muscles that usually have to compensate by being physiologically strong. So you think about how big your Achilles tendon is very close to your ankle, because it has to compensate by being so close. Or your bicep being so close to your elbow joint, it has to compensate by being very, very strong because it doesn't have the mechanical advantage of distance. So it has to compensate physiologically to try to make those motions happen. Sprinters can choose to jog. Slow people like me can't choose to sprint. So when you're doing something very heavy, you can't do it fast. Kind of common sense, right? If you're doing a max, it's going to go slow. So all hands on deck, first class muscles, second class muscles, third class, but everybody can help move it. If you're spotting someone, you don't have to get, if they're stuck, you don't have to push a lot to get them unstuck, right? However, when you're going fast, you're sprinting, when you're trying to move fast, usually it's not something heavy because you can't go fast and be heavy. So then it's third class arrangements, things that are inserted close to the axis that can make you go fast. All the distal inserted things in slow muscles, they're like, look, I'd love to run with you, but you're going too fast for me. Let me know if you slow it down. That kind of makes sense? Usain Bolt can choose to jog. I can't choose to sprint.
So you so much down to with the effort of the bonus.
Say that one more time.
Yeah.
This
So I assume the axis is the same as the pivot, right?
Pivot, axis, fulcrum.
So if the pivot is closest to the load, would it be?
Let's look at advantages and disadvantages. What advantage would the rock have? Speed or torque? Speed. And you know how I know? Because if I pull this down and let it go, small distance, huge sweeping range of motion.
So from the axis is further away, you take a lot more.
It's all about trade-offs. If the axis was closer to me, I would lose my advantage of torque. So in other words, again, what I love about this picture, it shows the different advantages of the different forces. Here, I have the advantage of torque, but if I'm going to move that rock, that boulder, it's going to take me a long distance to do it. But if I let go, I'm sure that rock can move it very fast. It's to show the two different trade-offs. If I move this closer and closer and closer to me, I'm going to lose my advantage in torque, but I'm going to gain an advantage of speed if I can move it. So you think about like a circus gymnast, when they're jumping to try to propel the person, they're not doing disadvantage because they want them to move fast. And usually it's like 5 or 6 gymnasts all jumping at the same time to create a lot of load. So it's just to show you the trade-offs. This rock would have the advantage of speed at the disadvantage of torque. The person would have the advantage of torque at the disadvantage of speed. That's how levers work. What you gain in one, you lose in the other. What's one in football? What's one of the common things? Well, I don't want to add too much weight because it might slow me down. I'm just saying, sometimes there's trade-offs, right? Like, and so with levers, it's very similar. There's certain trade-offs, there's certain advantages. It's like, being a specialist at certain things, right? You have certain muscles that have certain advantages because of how they cross, how it's
That's why I'm trying to use.
specialist. But it's all about, again, I'm not going to ask you to draw, analyze. I'm just going to say, what do third class muscle functions or third classes, what do they do well? What do they have the advantage of? What do seconds have the advantage of? Or I can get real tricky, and instead of saying what advantage do thirds have, I might get crazy and say what disadvantage do thirds have. It's two different forms of the same thing. It's just seeing if you know where the trade-offs are. We can't have it, we can't have it all. We got to make trade-offs with these systems. Did that summarize the pulleys?
Yeah, so what would be the advantage of two?
Of what?
Of
Sure. To show you, just for transparency, I'm going to literally pull up. Swatch. Trade, movement strategies, pulleys and levers. Pulleys can be used to create advantage in force, range of motion, or speed of movement. Type 1 is when we use a bone to create a better mechanical advantage inside the system. Who cares? Like maybe, I don't know if you go to optometry school, you'll learn about the little trochlea in the little eye, but not really applicable to what we're going to be doing in class. And so then I say, okay guys, look at the third. Instead of this bony thing being inside, literally the muscle comes down, wraps around the bone, and look at that new angle of pull. Look at that perpendicular pull that it would not have had if it came straight down. That's a pull. It's a way that we can change the angle. The fancy term is angle of inclination, but basically the angle of pull of a muscle. And so you have a muscle that's coming in flat, but by the time it wraps around this bone, now it's coming in at an angle, and now there's perpendicular pull to it for rotational components. And then the last one is when muscles can help improve an angular pull. And so on the test, I literally would just pull straight from there. It's like, all right, guys, which one does the muscle use another muscle to help its angular pull? Like it would literally just be examples so that you know the
second advantage, like that section.
second class will always have an advantage of torque at a disadvantage of speed. Thirds will always have advantage of speed as a disadvantage of torque.
So the lever is the insertion point, and then the pull is the angle where it enters that.
Yeah, they are kind of used interchangeably. Levers have to require more components than a pulley. Because like with leverage, you're looking at the axis, you're looking at our force, you're looking at our resistance, and you're kind of looking at the whole system. For a pulley, it's just what helps that muscle come in at a better specific pull of the movement, at a better angle of inclination to have more of a purpose. You guys are right. And I got one. Your body shrink wrap. Our skin, I can't have a muscle pull out of my skin. So all these muscles that cross, especially in anatomical, are very linear, right? Very stabilizing, not a lot rotary. So these little changes in pulleys to help give it a little bit better rotational pull. So it's more specific. That's why we start with levers and we go into it and say, hey, let's look at how we can change the specific angle of that muscle to make it less parallel and more riveting.
Okay, makes sense.
Yeah.
Just because this gets missed often, scalar, and vectors with terms.
Oh, yeah, I'm just gonna pull straight from your notes.
Notebook makes vector magnitude and direction versus scalar, a little bit simpler.
I would just, straight from your notes, I would just say, this is displacement scalar or vector. I mean, literally, you have a chart that says, here's your scalar terms and here's your vector terms.
I would know that one, and then no, Dr. Campbell's very simple ways of the three laws of motion. I think that, did you go over them?
Yeah.
Okay.
Inertia, F is equal to ma, and force counterforce. It's impossible to touch the desk without the desk touching you back. That's Newton's third law.